So we're revisiting the fundamental theorem of calculus. So we did the first part of it, and now we're going to do part two. This is like the sequel. Fundamental theorem of calculus is back. All right. So the first part I'm going to review. This is what we have done already. This is whenever you're doing the integral and then you do upper boundary minus lower boundary. That's your first part of your fundamental theorem of calculus. All right. And what this gives you is area under the curve. That is super important to know. It's called the fundamental theorem. All right, so area under the curve is what that gives you. And if you have integral from a to b of this derivative f prime, you do an antiderivative that would take you back to just f of x. Again, you need to come up with a function that if you did the derivative, you would get this. It would be f of x, and you do upper boundary minus lower boundary. And that is what gives you the area under the curve. That's review. That was the first half. That's what we've been doing for Unit 6 and Unit 7. That's your first part of the fundamental theorem of calculus. So integral of a derivative. So the second half of this is derivative of an integral. Now a derivative is a rate. So what this gives you is the rate at which the area is changing. Remember, a derivative is a rate of change. This is going to give you the rate at which the area is changing. And I'm going to write out a few ways that this can look before we get into the examples. They're all really versions of the same thing, but I like to write them out separately so you can see like if it looks like this is what's going to happen. And if it looks like this, then this is what's going to happen. All right, so these are all going to say d dx in front of them. Those are instructions that mean take the derivative with respect to x. And that's really important. You're going to see in a second because there's going to be an x and a t. You're doing the derivative with respect to x. All right, so if you have derivative with respect to x, integral a to b f of t dt, that is going to end up being 0. Because a and b are constants. So like if you have an integral from 2 to 7 and you find that area under the curve, you're going to just get a value. And the derivative of any value is just going to be 0. So if both of your boundaries are just numbers, then it's just going to be 0. The derivative of a value is 0. I don't know how else to say it. The derivative of a constant is 0. All right, now if it's derivative from a to x, f of t dt. All right, now I stuck a variable in there, but the derivative and the integral undo each other. They're inverses. So the derivative and the integral cancel out, and you just end up with f of x. So listen carefully. I'm explaining why this is like, derivative and integral, they cancel out and blah, blah, blah. But if you tune me out, literally all you do is take the x and plug it in for t. That's it. And what I usually tell my students is the only way you're going to mess up these problems is if you try to do anything. Like just don't do anything. Like you just take the x, plug it in for t, and that's it. Don't do a derivative. Don't do an integral. Don't put a plus c. Nothing. Like you literally just plug in x. That's it. Now, if we reverse the boundaries, so if you have that, well, let me ask you guys, when we reverse the boundaries, what do we put out front? Whenever I switched the boundaries, what did we do? Because we've actually done that before. Yeah, good. Thank you. Negative. It's going to be the opposite. Negative f of x. I was hoping to get more answers there. I don't know if we're tired this morning or like just looking forward to it being early release, but you switch the boundaries, it's just going to be opposite. So it'll be negative f of x. All right, and then the last way this can turn out is if you have not just x, but like its own function in there. So I'm writing g of x, but it could be any other function, x squared, sine of x, e to the x, x cubed plus 3x, something that's more than just x. That's going to involve a chain rule. So for this one, you just took x and plugged it in. You're going to really do the same thing here. You're just going to take g of x and plug it in. So you would have f of g of x. You just take that and plug it in. But then you have to chain on the derivative of the inside part. So you chain on g prime. And I'll sometimes write that first, just so I don't forget to put it. But it's just a chain rule. That's all that is. Yeah, so f of g of x, and then you chain on the derivative of that stuff. All right, so that's the part that takes the longest. You're going through these questions should actually be really quick because, again, you don't really do much. There's really not a whole lot of math here. All right, so derivative of the integral, we're just going to take x and plug it in. So this is going to give you x squared plus 4x minus 7. And if you're like, that's it, yep, that's it. All right, so for this one, we're just going to plug in x for these t's here. So it would give you x squared minus x. But because x is the lower boundary, we've switched them. This one's going to be negative. And you have to negative the whole thing. So I'm going to distribute the negative through there. So that'll be negative x squared plus x. Yeah, and someone just wrote to me privately in the chat, I feel like these topics are getting simpler. Yeah, and I did say this at one point, the second half of this class, in my opinion, is easier than the first half. I know easy and difficult's an opinion thing, but I do feel like this class gets easier as it goes along, because learning what on earth a derivative is in those first couple of units and limits, that really slams you. And then once you get the hang of that, it builds on itself, but once you get that under your belt, the rest of this, it kind of goes a little bit easier, is my opinion. All right, so this one's not just x. This is going to involve a chain rule. So oftentimes I'll just do the chain rule first. So you'd have to chain on the derivative of 5x, which would be 5. So I'm just going to put that first, and then you just take 5x and plug it in for t. So this would be e to the 5x. And then this one, oh yeah, and the same person said definitely it is less abstract. Yes, I think integrals are easier because they're less abstract. You're talking about an area of something, and that's very like hands-on and visual, like you can see that. Let me ask you guys this one. I want to get a few more answers here. What is the answer for this one going to be? This one won't be too difficult to type in the chat with like weird symbols or anything. Joseph, I think you looked at the next one down. We're looking at number 4. Good, negative sign of x, guys. It's negative because the x is the lower boundary. We switched them, and then you just take x and plug it in. So yeah, good, negative sign of x. And again, I think you were looking at this one. Hey guys, why is this one 0? Because that's the correct answer. There's like no work for that. Yeah, constant. Good, no x. Good, I like both those answers. No variable, it's constant. So derivative of a constant is 0. Right, so for here, this is more than just x. That means there's going to be a chain rule. And again, oftentimes I'll put that first so that I don't forget it. So we're going to have to chain on the derivative of x cubed, which would be 3x squared. And then you just take that x cubed and plug it in for t. So 3x squared times cosine of x cubed. All right, so on the back here, so first of all, we're going to need a negative because we've reversed the boundaries. The variable is down here. Then there's also a chain rule because this is more than just x. So we're going to have to chain on the derivative of x squared, which is 2x. So double whammy there. It was negative and there was a chain rule. And then after that, you just take x squared and plug it in for these t's. So if you plug in x squared here, you get x squared squared, which would be x to the 4th, and then plus 5x squared. And then I'm just going to distribute the negative 2x. So this will be negative 2x to the 5th minus 10x to the 3rd. All right, now this one has a variable in the upper boundary and the lower boundary. So we're just going to do upper boundary minus lower boundary. You're just going to plug them both in. So let me plug in the x plus 3 for t. So that is the upper bound. Oh wait, I got a question on the last one. Did I write something wrong? Wouldn't it be 5x cubed? No, it was x squared. I'm not sure. I'm sorry, I don't know how to answer that question. I'm not sure where you're getting a 5x cubed. It was x squared. So when you plug in the x squared for t, you would get 5x squared. And then I distributed the negative 2x through there. I'm trying to figure out. Oh, okay, cool. Because I do make mistakes. So I'm human. I do make mistakes. So please ask me. I was trying to figure out if I had a mistake there. No, this is the right answer. Okay, cool. All right, so this is the upper boundary. And then I'm going to do minus and then do the lower boundary. So I'm just going to plug in x for t. So this would be 2x minus 5. All right, so I'm going to distribute the negative sign there. Actually, I'm also going to distribute this too. Lots of algebra here. So this will be 2x plus 6 minus 5. And then distributing the negative, this will be minus 2x plus 5. And I want you to look through there and tell me what you guys notice. What is this final answer to the whole thing going to end up being? Yeah, good. It all cancels out and the answer to the whole thing is 6. That's nice. That happened because there's an x in the upper boundary and an x in the lower boundary. And so yes, that makes me happy too. It's just satisfying as an answer. All right, and then we've got a few that are worded like this. And I think we're going to need a calculator for one or the other of these. I think we might need a calculator for number 10. So if you have your calculator handy, go ahead and grab that. If not, you can kind of just follow along with me. All right, this says if f prime of t equals this, that's the derivative. Find f of 6 minus f of 4. This is a review of the first part of the fundamental theorem. When they say find f of 6 minus f of 4, what they're asking you to do is an integral from 4 to 6. That's where your mind needs to jump. They ask you f of something minus f of something else. That's an integral. This is fundamental theorem of calculus. So what they're asking us for is integral from 4 to 6 of this derivative. So when they ask you for this, this is what they're asking you for. So we're going to do the antiderivative and then upper boundary minus lower boundary. So this antiderivative would be t squared plus t. And again, we're going to do such that 4 to 6. And so we'll do upper boundary minus lower boundary. So if we plug in 6, let's see, that'll be 36 plus 6 minus, and then if we plug in 4, that's going to be 16 plus 4. And so let's see, this will be 42 minus 20. So 22 for that final answer. And then this one's essentially the same thing. It's just worded a little bit more strangely. They give you this f of t statement, and then g prime of t equals this, okay? It says find g of 7 minus g of 2. So this is what you want to focus on. This means fundamental theorem. It means we want to do an integral from 2 to 7, and this is g, so we want g prime to go in there. It's the same thing we did up here. F prime is what goes inside the integral, your derivative. All right, so this would be integral from 2 to 7, and then here's g prime. It's this thing right here. So it's going to be 5 minus t, and then times f of t, which is this thing. This problem is so weird, and they do stuff like that on the AP exam all the time. Like they'll give you this function in terms of another function, and it's not hard, but it's distracting, and it makes you feel like it knocks you off balance. Like, wait, did I miss something there? You didn't. They just are evil. So g prime is what goes in there, and it was 5 minus t times this f of t. Now I'm going to let us use our calculator for this. You could distribute this all together and then do an antiderivative and then do upper boundary minus lower boundary. But for the sake of time here, we're going to type it in. Also, using the calculator is a skill that we need, and it is good for us to review this. So let me ask you, who remembers where on earth I'm going to find this integral in my calculator? How do I type this in? Because we're actually going to use this a lot in Unit 8. Good. Math 9, nicely remembered, guys. Math 9. Math 9 is going to be your best friend for this unit. We're going to use it a lot. Okay, so you're going to have to get really comfortable with this. All right, so it's 2 to 7. Now I know it says T, but I'm going to type X because I have a variable key. It's just easier. And see these parentheses that are there already? That's like an extra set of parentheses around this whole thing. I'm still going to need to use my own parentheses for the stuff inside. Like I can't use theirs. All right, so it's going to be parenthesis 5 minus x, and then new parenthesis 3x squared minus 4x cubed, close parenthesis. So again, you have to do your own parentheses for these two. The ones I kind of bolded are the ones that the calculator gave in the first place. And then at the end, you have to put dx. It'll give you an error if you forget to put that last x in there. All right, and there's your answer. Now this decimal stopped, but hey guys, say it kept on going. How many decimal points do you need to put to get full credit? Good, you need 3. I don't know how to tell you this, but if you put 2 decimal points, like say this kept on going, and you only put 2 decimal points in the AP exam, they won't give you credit. Like you'll get no points. Like you either earn a point or fail to earn a point, and they will not give it to you. Like you will get a 0 on it. So please put 3 decimal points. Pretty.